Welcome to my YouTube channel. I will solve some questions from limit and continuity. So first example is prove that limit z tends to z0 f of z equal to z0 square where f of z equal to z square. So that is we have to prove limit z tends to z0 z square equal to z0 square. So this is very simple. As we put z equal to z0 we get z square equal to z0 square. So it is trivial from this we can see. So but we have to prove this. So to prove this we have to use the epsilon delta definition of limit. So what is that? So to prove this we have to find for any given epsilon greater than 0 we have to find delta that is dependent on epsilon greater than 0 such that z minus z square minus z0 square modulus less than epsilon whenever 0 less than z minus z0 less than delta. So we have to prove this. Whenever this we have to show this happen for given epsilon greater than 0. So we have to find delta. So then we can say limit z tends to z0 z square equal to z0 square. First if we take delta less or equal to 1, then we find z square minus if this, and for z minus z0 less than delta we get this value equal to z minus z0 z plus z0. So this can be written as z minus z0, that is z plus z0. So this is delta, so we can write this is delta and this can be written as z minus z0 plus 2 into z0. So from this we can write this is z minus z0 plus 2 into z0. So this can be written as 1 as we take. So from this we can write delta and this is 1 plus 2 modulus z0. So we have got this thing if delta less than 1 and this inequality hold. So using these two we get z square minus z0 square less than delta into this. If you choose delta as 1 or 1 by 1 2 1 plus 2 modulus z0 whichever smaller. So if we take delta as 1 or this whichever smaller, so we take smaller between these two and we put here get from this, that is z square minus z0 square less than, so delta into 1 by this 1 not 1, this is epsilon by this. So we get this is delta into epsilon by, so we put delta less than equal to this, so we put it, this is in place of delta and this is same, so this will be cancel out, so this is less than epsilon, that is this will be less than epsilon. So we show this for this inequality. So from this we can say limit z tends to z0 z square equal to z0 square. This is the proof. So we have to show this by epsilon delta definition. Now we solve another question. Example 2. Examine the continuity of this function f of z defined as z square when z equal to z not equal to z0 and 0 when z equal to z0 at this point. So we have to find, we have to examine this function is continuous or not at this point. So as we know that we get limit z tends to z0 f of z equal to z0 square when f of z equal to z square. So if we exclude this point z equal to z0 from the definition, this will be same, this function will be same as this function. So limit at z tends to z0 f of z of this function also equal to this, so the value will be same. So at z tends to z0 f of z will be z0 square, but to be continuous at z equal to z0 this should be equal to f of z0, but for this function f of z0 is given equal to 0, which is not equal with this, which is not equal with this limit. So this function is not continuous at this point. So to be continuous, a function is continuous if f of z0 is exist. This limit z tends to z0 f of z exist and equal to this value. But for this function, limit not equal to the value at this point, as this is equal to z0 square and this is equal to 0 given. So this function is not continuous at z equal to z0. But if we redefine this is as z0 square, so this function will be continuous. So in this case, z0 is called removable discontinuity of f of z equal to this function z square when z not equal to z0, and this is 0 when z equal to z0. So for this function z0 is removable discontinuity. We have discussed in the previous lecture what is removable discontinuity, whatever, how can we define this such that it should be continuous. So we have to just put the value of the limit for z equal to z0, then this function will be continuous. The given function this is not continuous at this point, so this was the problem. I will discuss another example. Now I solve example 3. So suppose that limit z tends to z0 f of z exists. Prove that the limit, so this limit must be unique. So we have to prove basically a theorem. Whenever the limit of a function is exist, it is unique. This is the theorem. If we can show limit z tends to z0 f of z equal to L1 and limit z tends to z0 f of z equal to L2, then we have to show that L1 equal to L2. So if we can prove this by taking this and which imply this, we can say limit will be same. So first take two limits are there for this function. So by epsilon delta definition, from this we can write f of z minus L1 less than epsilon by 2 whenever 0 less than z minus z0 less than delta, and this is also minus L2 minus epsilon by 2 whenever 0 z minus z0 less than delta. So these two happen whenever we consider this limit equal to L1 and L2. So from this we have to show L1 equal to L2. So now to find this value L1 minus L2, so this can be written as L1 minus fz plus fz minus L2. So this can be as L1 minus fz plus fz minus L2. As we know, modulus A1 plus A2 less or equal to modulus A1 plus modulus A2. So we apply this formula here. So it can be written as fz minus L1 and this is fz minus L2. So by putting this value, we get epsilon by 2, that is less or equal to epsilon by 2. This is epsilon by 2. So this becomes epsilon. So generally we get L1 minus L2 less than epsilon whenever this happens. As so from this we can write whenever this, so we get this less than epsilon whenever this happens. So as epsilon is very small, so we can take L1 minus L2 is less than any positive number epsilon however small. So this can be written as L1 minus L2 equal to 0. So from this we get L1 equal to L2. So we assume that this is exist which is equal to 1 L1 and we take another limit which is equal to L2. So simply we by calculating and using the epsilon delta definition, we prove that L1 equal to L2. So this proves that the uniqueness of limit. If limit of a function exists, it must be unique. So this is the theorem. So if you like it, please follow my YouTube channel and share with your friends so that they can also be benefited by my lectures. And these are all previous year questions for complex analysis, that is MA 201 for the students of Triple IT Bhagalpur. So if you like it, please subscribe my channel. Thank you very much.